1.55, bases other than e and applications. So we're going to start out by looking at the definition of exponential function to base a. So that sounds really confusing. It says if a is a positive real number, so a is not equal to 1 and x is any real number, then the exponential function to the base a is denoted by a to the x and is defined by, okay, so basically what I'm going to do here is I'm going to rewrite this a to the x using the natural exponential function. So I'm going to write that a to the x, my pen might be dead here, a to the x is equal to e to the natural log of a to the x. So this is true because I know that e and natural log are inverses and cancel each other out. And so it's really just a to the x is a to the x. Okay, so that's what we have so far. But remember, we're going to be doing some rewriting stuff here. So e natural log a to the x. And then we know our exponent, our log properties, I should say, means I can take this exponent and I can multiply it in the front. So I could write as x times natural log a, or I could write it as natural log a times x. So those are equivalent. So the reason that we need to know this is so that we can figure out how to take the derivative of a to the x, okay? And we'll look at that in a minute. And it does say here if a equals 1, then y equals 1 to the x power, which equals 1. It is a constant fraction. So next we're going to look at what happens when we have a natural log and we're trying to change that to some other base. So if I have, let's see, log base a of x, I guess other way around, right? We are looking at something that's log base a of x. We're trying to make it into a natural log because we know how natural logs work. So let's remember back to Algebra 2 and pre-calc where we did change of base. And we always said you can make it into whatever log you want, but it's going to be log base whatever you want of the big number. And we said big number because it was written and it looked bigger over log of the little number, which was a. But because we really like natural logs, we're not going to do this with base 10 like we did a lot before. We're going to do this with natural log because natural logs are super easy. I didn't like the way that x looked. So I'm going to write this as the natural log of x over the natural log of a. And that was just a way to change the base because I needed to evaluate a log and I didn't have whatever base a was. Now I'm going to rewrite that as 1 over the natural log of a. I said a, but I wrote an x. And then times natural log x. And the reason we're going to need this again is to do derivatives. So a little bit of review. I want to solve each equation. There are lots of different ways of doing these. One way on this one would be to log both sides. Because I can tell that 81 is a power of 3, I probably wouldn't do that. So I could write log base 3 of 3 to the x is log base 3 of 180 first, and I could simplify that. But I could also just say, well, 81 is 3 to the 4th power because it's in the denominator. It's really 3 to the negative 4 power, and then x equals negative 4. So that other way I alluded to is pretty much the same thing. We would just have to say that 180 first is 3 to the negative 4 power. Log base 3 of 3 is just going to cancel out. We'd get negative 4. So they're both the same thing. I really like the first way I did it a little bit better. The second one says log base 2. So two ways of doing this problem. One is just, hey, this is a log base 2. So let's exponentiate both sides, use raisins. So raise both sides as a power of 2. And then log base 2, 2 to the log base 2, like that's gone. We just have x. Those are inverses. And that gives me 16. Another way to work this one out is just to change it to exponential form. And so to change it to exponential form, my base is 2. I raise it to the negative 4th power. It equals x. And so Why did I have a negative there and I didn't here? Okay, I'm going to have to fix this. That's going to be 1/16 is equal to x. So obviously I did something wrong the first time and it looks like I just didn't copy this down. And so it'd be 1/16 as well. So maybe it's a good thing I did that problem twice. We don't care in calculus how you're solving as long as you're getting the right answer, unless you're asked to use a certain method. Okay, so I'm taking my derivative of a to the x power. So I want to remember that up above I wrote a to the x as a to the x. You can tell it's late at night and I'm tired and I feel like I'm making mistakes. A to the x, I wrote that as e to the power of natural log a to the x, because the e and the natural log would essentially cancel out. Those are equivalent. So I want to think about how I can rewrite it that way. And then I want to think how to take a derivative of that. Well, to take a derivative of anything that's e to a power, I rewrite e to that power. So let's do derivative and derivative. But again, this is just going to be my scratch work right now. So I don't think I want to write it in here yet. So when I take a derivative of that, I would rewrite all of it, e to the power of natural log of a to the x power times, and then I would do my derivative of the exponent. Well, the exponent is natural log a to the x. And so really though, that's just that x times natural log a. So x times a constant is just going to be that constant. Okay? And then these two cancel out. So really this derivative is just a to the x times natural log a. And we should probably have the natural log a written in the front because it's just a constant. I'm telling you, like the mistakes tonight, it's real. It's like 10 o'clock at night. If I had a derivative of a to the u power, it's almost the same. Natural log a to the u, and then I have to remember my u prime. So that's just my chain rule version. And kind of working the backwards, if I want to integrate a to the x power, well, when I take a derivative, I'm multiplying by that natural log a. So if I'm taking an integral, I'm dividing by it. So it's going to be 1 over natural log a times a to the x power plus c. Okay, over here I want to figure out my derivative of log base a of x, and so I want to think about how I can rewrite that one as 1 over natural log of a times natural log x. So then let's go ahead and look at how I would take the derivative of that guy, right? So to take the derivative of that, this is just a constant. 1 over natural log a is a constant. So I would just want to rewrite that. And then my derivative of my derivative of natural log x is just 1 over x. And then I'd have to multiply them. So what I'm going to write here for my derivative of log base a of x is just 1 over natural log of a times x. And then, of course, this one's going to be almost the same, but it'll be times u prime. So that's just my chain rule version. And I want to erase all of this scratch work. You can just memorize the derivative, okay? There's nothing wrong with that. I just have found that these derivatives were always kind of tricky for me to remember unless I remembered how I got them, because it's really fast for me to go through and think of it in terms of e or natural log and just kind of figure out what those derivatives are. So now we're going to use these derivatives. If I have 2 to the x power, how does that work? Well, if I'm doing 2 to the x power, I'm using this derivative rule right here. So because it's base a, I'm going to write natural log of 2. So let's write y prime equals. So I'm going to have a natural log of 2 and then times, and then it says a to the x power. Well, that's 2 to the x power. So I think these are a little bit clunky. They feel kind of weird. But we can totally do this. The second one is going to be this right here where I've got a to the u power. I have an exponent there that's not just an x. So I'm going to have to do chain rule. So y prime equals, and again my base is 2. So I'm going to write natural log of 2 times, and then I'm going to have the 2 to the 3x power, and then times, and then I'm going to take my derivative of my exponent, which is 3x. So now I just have a 3. So this is going to be 3 times natural log of 2 times 2 to the 3x power. My last one, I have log base 10. So log base 10 is just log. We kind of put the 10 in there maybe to help you out. So you would be thinking about how this a right here is a 10. So if I want to think about how to, it's really the chain rule version though, right? So really looking at this one. So y prime is going to equal 1 over natural log of, my base is 10, so natural log 10, and then whatever my u is, well, my u is that cosine x, and this is definitely the word cosine, and then times my derivative of cosine is negative sine x. There's a couple different ways we could go about simplifying this one. The best way is probably to think of this as 1 over natural log 10, and then think of this as negative sine x over cosine x, and negative sine over cosine would be negative tangent. So I can just do one more step and make this equal to negative tangent x over natural log of 10. I feel like that natural log 10 looks really weird. All right, next we're going to go ahead and integrate 2 to the x power dx. So remember, if we take that 2 to the x power and we take a derivative, right, we have natural log 2 times 2 to the x. So when we integrate, we're working the opposite direction. So instead of multiplying by a natural log 2, I'm going to divide by natural log 2. So this is going to be 1 over natural log of 2 times 2 to the x plus c. And we're just using that straight up integral property on this. So having all of these new derivatives helps us to take some weird derivatives as well. So we're going to go through and we're going to take a derivative on all of these. This last one, it doesn't say take a derivative, but we're going to be taking a derivative there as well. So if I have a derivative of e to the e power, it looks kind of weird. It looks impossible, but remember, e is just a constant. So I'm going to make a note here, e is a constant. And so when I say e to the e power, it's just a constant. The derivative of any constant is going to be equal to 0. This derivative of e to the x power, we already know that one. That one's e to the x power. This is just a trick. It looks weird because there's an e in there, but remember, it's x raised to a power, like a 3 or a 4 or anything else. We're just using that power rule. So this is just old stuff, right? We know that we're always going to take whatever that exponent is, multiply it in front, and then we're going to subtract 1 from the exponent. So it's just straight up exponents like we're used to doing. It's just the e makes it look tricky. This last one, in order to take a derivative, I would have to use logarithmic differentiation. I really like this application. So natural log y is equal to natural log of x to the x power. And that allows us to rewrite this x here, that exponent, as a number multiplied in front of the log, or an x multiplied in front of the log. I don't even really know how to say that right now. And then now that I have it like this, I can take a derivative. So when I take a derivative of natural log y, I get y prime over y. I accidentally switched colors there. And then x times natural log x, I would have to go ahead and do product rule. So x times derivative of natural log is 1 over x plus natural log x times derivative of x is just 1. So y prime over y is equal to x times 1 over x is 1. And then natural log x. I'd want to multiply both sides by y now. It's okay that this problem's taking up so much space. I knew I had room. So y prime is going to equal y times 1 plus natural log x. And then I want to substitute y in there. Y was x to the x power. So kind of cool how that one works out. And I don't know of another way you could do this besides logarithmic differentiation. So really that x being both the base and the exponent was a problem, but logs allow us to change that so that we don't have an exponent with a base like that, so that we're multiplying instead. So a couple of new limit theorems that are kind of interesting. So think about this. I take 1 and I add 1 over x, and I do this a bunch of times, right? As x approaches infinity. So as I do that close to 1,000 times, I end up with e. And I think that's just really cool. And the reason that these are equivalent is because those fractions are equivalent. So if I have 1 plus 1 over x, and I multiply this first thing by x over x to get a common denominator. Now I have x plus 1 over x. So the fractions are just equivalent. It's just different ways of writing it. But it's really cool to me that that just approaches e. So e is one of those numbers. Hopefully your pre-calc and algebra 2 teachers talk to you about this. It just kind of pops up all the time in nature and in banking, and it's just really cool. All right, I feel like these notes were pretty short and sweet. I find that these are really hard derivatives and integrals to memorize. You're really going to have to work on these ones. Hopefully me showing you where they come from helps a little bit, though I feel like I was writing kind of messy and making mistakes tonight. As always, if you need any help, please make sure you ask.